recorded. It was like, oh, he told Master Gandhi to play something, so he wants to vibe on it. So most of the vibe is from him. And then he was like, let's try, let's do something. So it just happened. And was it intimidating? Stonebwoy is very friendly. I think that's one thing people don't know. And he's very playful. So it wasn't very intimidating. It was more of like an elder brother and a younger sister. Oh, do it like this, come on, do it in the studio. The kind of things that he would say and all those things like, oh, I wouldn't make it, that sort of thing. And I said, I don't want you to take that song.
Mm, Good evening, everyone. Please, I believe you can hear my voice clearly. If you can hear my voice clearly, please give a reaction. Yeah, Mr. Justice. Okay, so those who are present, let's just go ahead and then start the session. Okay. Yeah, you said you want a free class. We've offered a free class, and then looks like they are still joining late. Let's just move on. So without wasting any time, we are just going to dive right into the assignments, and then we'll go as far as possible before the lesson ends. So yes, Mr. Jacob Frank.
Please, good evening.
Good evening.
Please, some of us, like me, for instance, I'm not with my machine, so I think this session is being recorded, right?
It says
Is it, please?
yes, it is. Yeah,
Okay. So please, when the sessions end, then you can send it to the group for us. Well.
yeah. We do that. I
Thank
believe we
you.
do that.
Thank you, boss.
Right. Okay. Let's dive right into it. So the assignment overview says you need to, it is evaluating how much you understand from your readings of the first few chapters between chapter 1.1 and 1.4 of the Stallings manual, and then the performance concepts in chapter 2 of the same Stallings manual. Understanding of the von Neumann architecture, fetch code, fetch decode and execute cycle of the CPU, the registers, instruction flow and control, and then performance metrics like the CPI, sorry, clock rates, the execution time, Amdahl's law, cycles per instruction, etc., etc. It also goes further to say that we should use exactly this central Littleman computer simulator, the Peter Higginson's model, the one displayed on the right side of the screen. Joshua, please help me remind the elite farm members that the session has begun, so they should join in.
Okay, sir. Okay, sir.
And
Sure.
yeah, and then the CPU OS simulator that was provided, so you need to boot all this in on your PC and then you follow along. Right. So first activity says that we are to enter the following Littleman computer program into our simulator. So enter them at once. Let's just do this. Let's just follow it on the dots. We'll just be changing phrasing, and then by in the end, they will still be using the same instructions. So if you follow through this one just as this, then you will just have to post that very same thing into your Littleman computer setup. Okay. So once you paste that there, you can go ahead and submit. You can modify that instruction so that it specifically reserves the memory address 20 for the data value that you will store. Since if you check the instructions carefully from my lessons yesterday, you see that it says 20 here and then add 20 here. It means the memory address that are being used for the data is the memory address 20. So you can assign address 20 to the data. Let's submit this, and then it is taken into our machine as the code to be executed. So now it says that we have to run the program, and when we run it, we have to use these exact inputs. The first input should be +7. The second input should be -7. And we should only use the step button. So we should step it once at a time without running. We should step it one at a time. And when we step it at every step, we have to look at the program counter value, the particular instruction at that step, the instruction register. Yeah, sorry, please, who is speaking? Right. The instruction register that combines the operation code, the opcode, and then the address, right? We have to take a look at that too. And then we look at the accumulator before the execution and the accumulator after the execution. And we are also supposed to take close notes of the mailboxes that will change during runtime. Okay. So when we load the instruction into the code, you're going to realize that by default, some mailboxes had already changed. So we have not yet started our execution yet. But some mailboxes have changed. They have nothing to do with the stepping that we'll be doing as the various steps. So you do not include them as the mailboxes that change during runtime. Some of the mailboxes that I'm talking about currently include the 0, 1, 2, 3, 4, 5, and then the set one, 7 and 8 as well. By the von Neumann architecture, we know that data and the instructions are stored in the same memory addresses. Therefore, these memory addresses are being used to hold these instructions according to how they have been ordered. That's why these ones have been stored. So do not get confused. Do not use those memory spaces as the mailboxes that will change during runtime. That one strictly has to do with when you are stepping the program. Now, let's follow what the program says. So let's step it and then we fill our table accordingly. So I'm just going to fill and then you can follow my lead. Okay. So we can step it. Let's first reset our simulator. Please, if you have any question, unmute and then interrupt me, but politely, and then ask, because I am using all of my screen right now, so I won't be displaying regions of the charts and all that for interactions. So you understand what I'm saying? Let's proceed. So let's start reset the program first, and then we step it one by one. So reset program, and then we step. So observe the changes carefully, people. So upon the first step, good. So upon the first step, we are supposed to write a step number. That's the first step. So step 1, the program counter incremented towards 1. The instruction at that step is what is stored in the instruction register, right? So then the instruction for the instruction is supposed to be input. That's the instruction we are using. So that's INP. You input that into your table. Okay. Yeah, yesterday I mentioned those who were here that my keyboard has been fried. So some of the keys are not functioning. So I'll be using the on-screen keyboard alongside. One of the keys is the P key. So you write INP for inputs, okay, not IN. My P is not working, as I mentioned earlier. I could copy one and paste it there. Yes, but you write INP for inputs. So that's the instruction. Now it says the opcode plus the address. Remember yesterday I explained what the opcode has. It has a combination of the opcode itself, and it also has the operand. The operand becomes the what we are using for that execution. So if it's an address, then that address becomes the operand. If it's a data value, then that becomes the operand. Mostly it will be addresses. So how can we get this for this one? Come to the instruction register and take the opcode from there. The opcode is 9. And then 9 corresponds to the inputs instruction. And then the address that we are using for that is address 01. So you will write the opcode plus the address here as 901 inside your table. And then for the accumulator before, so currently the accumulator holds no value, it is at 0. So you put that at 0. So before execution, now let's input our data value here. And then we continue the stepping. So it says we have to enter +7 first, right? So on your keyboard, you press +7 and you hit enter. Once you hit enter, there's a change in the accumulator, right? So AC after you step, it increments from 0 to 7. You enter that at the AC after column. And during this stage, has there been a change to any mailbox? The answer is no. All the mailboxes, how they started 901, 320, 901, blah, 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 all the way to the end, they have maintained their values. None of the mailboxes have changed yet. So there has not been a change to any of the registers or mailboxes. The RAM space is good. So then mailbox change, you can say no, or you can say none. So none of the mailboxes changed yet. Let's continue the stepping of the program. All right. So then after we stepped the program the second time, let's see the changes that have happened. So you increment your number of steps to step 2. The program counter has now changed from 01 to 02. Holding the instruction for the next and the address for the next instruction. The instruction this time was store. You can write all of the instruction there, store 20, store address 20, and then the opcode plus address will be 3 for the opcode, and then the address 20 for the address that we are storing in. The accumulator before was 7, and then afterward the accumulator still remained 7. Fill the table accordingly. And then the mailbox that changed during this time, there is a change. Since we store data in address 20, the data was moved to address 20, as you can see here. So address 20 has been written during this step. So what the program basically did is it read data and then it has now stored it inside address 20. So in address 20, that's the mailbox that changed. So you write that in your table. Let's proceed. Step 3. So yeah, whoever has their mic on, please, I beg you, mute it. Today I'm a little tired, so you can even hear my voice. Okay. So if we step it a third time, let's see what happens. Oh, sorry, the program is not responding to my step, so let me reset it and then start over again, okay? So I step. That was the first step we did. We have already written it, so let me just redo it. We enter our inputs. We entered +7, you hit enter, program goes, we step it again. Program counter increments from 1 to 2, and waits the next one. So data is read, and then it's sent to address 20, right? So now let's step it for the third time. When we step it the third time, right? So after we step it the third time, what have we seen? Program counter increments to 3. So 03. Oh no. And then the instruction for that step is still input again. So you hit that in inputs. And then the address and then the opcode for that is 901, as you can read from the memory address register and then the instruction register. The accumulator before was 7, and then the accumulator after. So we are going to enter our second value at this point, right? So it is asking us to enter an input. You can see it has pointed to this side. It says input required here. So then we are going to enter our inputs here. Since the question said the next input should be -7, you also enter your -7 inside your code. So -7. And then you hit enter. After doing that, look for changes. Okay, so then look for changes in your accumulator. So before runtime it was 7. After stepping it again, it becomes what? So the accumulator has now changed from 7 to -7. Which of the mailboxes changed? So has there been any change in any mailbox? The answer is no. So none of the mailboxes have changed yet. So you write that none have changed. Then we move on to the next instruction at address 4. And the program counter, okay, so let's step it again. Right. So then after we step this again, this time, look at what has happened. So yes, our program counter is now holding address of the next instruction on address 4. So let's put that there for the program counter 04. And then the instruction at that point says add 20. So we write add 20. The address and then the opcode is 120. 1 for the opcode, and then which is for add, and then 20 for the address. So you are going to need to do these, say these things when you are doing the cycles explanation and all that. So I am saying it so that you also follow in the order. So add 20, the 120 you see, the 1 is for the add instruction, that's the opcode, and 20 is for the address that we are adding or we are using for the addition. So the accumulator before then was what? 7, -7. But after we executed that instruction, it has now changed to 0 because 7 plus -7 is still 0. And then is there a change in any of the addresses? The answer is no. None of them changes. The first one is man or not man. All right. We move on to line 5 where there is a fifth instruction. Let's execute this and see what happens. So then at this point, something interesting happens. So let's follow through with that. At step 5, the program counter has now updated towards 8. The add instruction has now been executed in the previous level, but then the instruction at this point was BRZ08, as you can see here. So the instruction here was branch if 0 to address 8. So then we write that. So yesterday we looked at this instruction and we know that it's the branch if there is a 0 instruction. And this one says branch to address 8 if there is a 0. And then once at address 8, the IR and then the opcode is 7. The opcode and then the address is 7 and then 08. So that's 708. And then the accumulator before was 0. And then the accumulator after was still 0. Did any of the addresses change? The correct answer is none of them changed. So we enter none. Then we move on to the next one. So we step again. It says for at least 10 steps. So let's keep stepping. Now in the next few steps, you're going to notice something interesting. So now look here. Program counter increments from 8. So we're on step 6. It moves to 9. After it moves to 9, the instruction at 9 is unknown. So since there is no instruction at 9, we do not know what to enter there, so we can say there is none. Then you write with the right syntax, capital or small letter evidence syntax. Then we come to the opcode plus address. As you can see, it's all zeros. And then we come to the AC before is 0, AC after is 0, mailbox that change is just none. This particular thing cycle is going to repeat, and the only things you are going to be incrementing at this point are your steps. So it increases to step 7, and also your program counter value is will increase to step value 10 as you go further. And then will there be an instruction? There will be none. So we can keep stepping it, and then you will see why. And there is a good explanation as to why this happened. Okay. And then we step again. It increments to 11. Yes, Abuaje friends.
Yeah, thank you. Please, the hot. What line is the hot at? Isn't it at line 8?
It's at line 7.
Line 7 instead.
That's right.
Okay.
Should I zoom in on
Thank you.
the instruction? Yes. So here is it. So at address 7, you hold the halt instruction. So no, it's not at address 6. Okay. All right. Let's proceed. So then you keep stepping and stepping and stepping. You will keep repeating this line. So you increment your step number and then your program counter number. The instructions will still stay none because no instruction is being executed at this step. The address and opcode will be 0, accumulator before 0, accumulator after 0. And the mailbox that changed in this instance will still be none. So after you have completed the table, there are some questions that you are supposed to answer. So let's write down the answers to these ones, and then we will rephrase them into proper ways and then use them in our assignment. So I'm just here to help you. I'm not here to blindly left answers for you. So it says, at which step did the branch instruction execute? So the branch instruction executed at which step? The initial branch instruction was here, branch 0 at 08, and that should have happened at step 5, right? So it happened at step 5. The branch instruction executed at step 5. And then this happened because the conditions for that branch was that if the result or if the result of the operation is a 0, jump to memory address 8. You see that. So the little man computer followed what that branch instruction said and then ignored what the program counter was doing by incrementing sequentially. Instead of following the sequence of increments and going from 8 to 9, or instead of going from 4 to 5, sorry, last in from the add address to the 5, it rather jumped back to address 8 or moved forward to address 8. So then at which step did the branching instruction execute? It's executed at step 5 after the add instruction. Why did the program counter not increment normally at that step? So the answer is that the branch instruction overwrote the program counter value. And then this caused the program counter to jump to instruction to address 8 in the memory address register. So the branch instruction overwrote the program counter value, breaking the sequence, forcing it to jump to the, Identify when memory was read. Now, memory was read a couple of times. However, the one the question is pointing to is when data was read from memory. Because if you want to know when memory was read, actually every single time we took an instruction, the memory was read for the instruction was retrieved, brought to the operational unit, the control unit broke it into the instruction and then the address. So every single time it was read. But this one is targeting. The way the follow-up question is saying when was memory written. So then it is actually following on that very same question. Therefore, it is only asking about when data was read and when data was written into memory. So when was data read into memory? So if we trace our table carefully, the data reading happened when we stored a value in memory and then we went to read over it, right? So then when we did the storage here, that was a writing. But when was data read into memory? Can you tell me when data was read into memory? Is there any amongst us who can share with us when the reading of data was done?
Is it add 20?
Come again.
Add 20.
Is it add 20?
Where we
Okay,
when we
so
inputted and added.
okay. So then he says at the add step, data was read. And what this means is that the central processing unit sends a command, and then the memory address register indicated a particular address 20. Then the control bus carried what was stored in address 20 to the memory buffer register. So the address bus carried that to the memory buffer register, or the memory data register, and this will do the addition for us at that side. So yes, reading was indeed done at that point. And then when was memory written? Memory was written during the store instruction. Okay, so at store 20. So during the store instruction at step 2, that is when memory was written. So memory was read during step 4 as the add instruction, and memory was written at step 2 during the store instruction, or the instruction STA20, and then etc. etc. So use your desired set of vocabulary. I'm giving you options so that your works will differ in case the lecturer truly checks for detail and all that. All right, so let's move on. Explain how this program demonstrates the von Neumann model. So the von Neumann architecture is all about how programs and then instructions and data are all held in the same memory space, and then the CPU simultaneously uses these same addresses to execute the programs, right? So let's explain how this program demonstrates the von Neumann model. So it is realized that in the same mailboxes that we were storing data, the instructions that were inputted first were stored sequentially inside the mailboxes, starting from mailbox 0, followed all the way to mailbox 8. So that very same spaces where we held our data, the CPU, the LMC, Little Man Computer, stored the instructions there as well. And if we go further to an address like address 20, currently the data that we inputted is also being held in address 20007. So this is the shared storage concept according to the von Neumann model, which says that data and instructions are all stored in the same memory addresses. Is that clear? So then this is how it explains it. So you explain by saying that the instructions that were entered into the program were stored in order, starting from address 0 to address 8. And then the same addresses or the same RAM spaces were used to hold the data later at address 20. And this demonstrates the shared data or the shared storage concept of the von Neumann architecture. That's basically it for that. All right. Part B. It says we have to modify the program so that the system continuously accepts numbers. It stops only when the user enters a 0. It outputs the cumulative sum before halting. Okay, so we are supposed to work on the program so that it changes its nature. It should be able to continuously accept numbers and accept until the user adds 0. Now, when the user enters a 0, the program is supposed to display all the sum of all the numbers the user entered before the 0 was added, before it halts. So then it says it has given us some constraints that we must still use the branch if 0 instruction and then the branch always instruction. And it says we must use only one memory location. This means we are only going to store the data and then retrieve the data from a single memory location. And we must demonstrate the looping clearly. It also says that we should provide evidence. So I want you all to take a screenshot. So after we edit our code, you edit your code on your computer. After you edit your code, don't take a screenshot of my screen. No, you see, I don't know how meticulous the lecturer is going to be. Maybe he might not. Yes, Auntie Monica.
Please, I didn't hear when you were talking about the BRC and the BRA. Did you say we should use one or we should use both of them?
You are using both. It says end, so you will use both. Okay. If you use one, your head's here. So you use both. It says use the BRZ and BRA. So you're supposed to use both of them. Okay. Exactly. Madam Mama.
Yes, it's
Okay.
clear.
Okay. Yeah. Right. So yes, please, ladies and gentlemen, use both. Okay. The way I'm here, small thing, I will sleep. Okay. Right, so you are using both, and it also says we should use only one memory location, so let's keep that in mind. It also says that we should take a screenshot before we execute the program. So after we edit the code, after you edit the code on your PC, take a screenshot of it. You are going to add that to your document, okay? So if you have prepared your answer documents, once you take the screenshots, in order to avoid stress, paste it immediately so that you won't have to later go through all the shots you have taken and start ordering them. But if you like, you can take the shots and then save them later and then come and then order them too. That's just another thing. But just do as you see fit. So, and we have to demonstrate the looping clearly. So after we take the screenshot for execution, after we run the program, when it gets to the looping instruction, we take another shot of that. And then we screenshots at termination too. So after the program has halted, we take a screenshot too. And then you will write explanation of the PC behavior during the loop. So how did the program counter behave? Did it increment sequentially or it started jumping to random or started jumping to particular or assigned addresses? And then how did the accumulator update during this runtime? And how were the memory spaces being used as well? We talk about that. So take note of all these things as we do the running. So I'm going to allow you to show me your creativity. Give us ideas as to how we can modify this code. Let's not waste time on this, just like a one minute something so that we can do more things. So a suggestion as to how we can modify this code to cause it to be looping, summing up all the data the user will add until the user eventually adds, until the user eventually enters a 0. Yesterday, we did a loop instruction that breaks when the user enters a 0, right? Can you get more creative and then even modify that idea further? And then let's see how we can modify this program to do exactly that. This time, we're not only looping, but we're also adding in every loop and storing the instruction that we are adding. Then we top it up after the next loop until you enter 0, and then we display that. Yeah, it was Prince Abuaje. Abuaje
So
Prince.
what I tried doing was I placed branch if 0 after the first input. So
Okay.
branch to line 8 if 0. Then I
Branch
placed another
to
one,
8. All right. Yeah,
branch
please
to
go
8 if 0.
Yeah. All right.
Then I placed another branch to 8 if 0 after the second input.
Oh, okay. So branch to 8 if 0 and then branch to 8 if 0 again after the second input. All right. So then
Yes.
so what you are saying is we take this particular instruction and then we put that same instruction under the first input, right? Right?
Yes, please. Yes, please.
Okay. All right. So please, when you did that, was it able to do as the program demanded? Were you able to keep summing up until a zero was entered, and after the zero was entered, did it display the outputs as desired?
Yes. So it keeps on adding, and then when you enter zero, either at the first input or at the second input, it just branch to the hot, and then the program stops. I don't know
Oh,
if
okay.
I'm following the instructions well.
Oh yeah, you are. That's very, but it displayed the sum as well, right?
Yes, it did the same as well.
Oh, okay. So then let's use his. It's a very interesting way of going about it. So let's do that. So he says after his first input, he came to put a branch if zero instruction to tell the program that if it encounters a zero during runtime, it should branch. And then he came to do the very same thing. Okay, this one is already there, so he did the same thing on that side. And then it kept adding, and then it displayed the sum output. Let's see about that. Okay, so what this program does is it takes an input, it stores the input in 20. It takes another input. If that input is 0, oh, okay, after the first input, sorry, I didn't do it for the second input too, right? So so does that mean that you deleted the second branch or the initial branch instruction from where it used to be? Am I getting that right?
Exactly. Exactly.
Okay. All right. So we take an input. If the input is 0, the program immediately jumps to address 8 and then the halts. There's a problem with this particular code, but because it won't be able to do what the person is asking, but it's still a very interesting way to go about it. So let's run this one first, see what it does, and when we are done, I'll take ideas from you again. If one more person can, but if we can't, then we just look at how best it will be to do it. Okay, so reset, and let's run it this time so that it moves fast. We don't have. Okay, so when we run it, it's asking for an input. We enter the inputs. Let's enter 5. Let's use a phase number so that we can observe the increments easily. So 5 is stored in the accumulator. It runs again. It asks for input. So this time when we put the 5 inside, the program went and came to line 7 and it branched back to 0, 0 because we've not entered the 0 yet. After we hit enter, the accumulator increases to 8. You put a 5 in there, hit enter. Accumulator has now increased to 5. Something interesting just happened. So, Mr. Prince, I think there is a little flaw in your program. The flaw is that the program will not really be able to display the accumulated output as you are saying. Currently, what it is displaying is separate sums of two numbers at a time. But the question is requesting that it will display all the accumulated sums. So you see all these numbers we have entered, it should actually display a 30. This still does display a sum, and it's a very interesting way of thinking. Nice. All right. That's good. So that's a good one. So now looking at what our brother has suggested, is there someone amongst us who has like from his what's his instruction, being inspired with something that might actually meet the requirements of the question? Hey, is that okay? All right. Let's see how we can do it. So thank you, Mr. Prince, for the suggestion. So now let's see what we can do to make the code do exactly what the program wants. The program wants us to, 1, take inputs. After taking inputs, it wants us to somehow keep that input for the next time an input will be taken. And when that input is taken, it is combined with the first input it is also preserved. When another input is taken, it is combined with the previous inputs, and then it is also preserved. It will keep combining and piling them up until you enter a 0. When you enter a 0, it is going to now display your sum. And after displaying your sum, it will now halt. Okay, so then let's see the modifications we can make to the program. So first off, we are going to have to take inputs, right? And then after we take the inputs, and then we cycle through all the way to the end. So the inputs there, we are bound to take it. So let's maintain that line that says inputs. Now, after we take the inputs, if it is a 0, then we will branch. But if we use branch to line 8, it means the program will be jumping straight to the halt instruction if the input happens to be a 0. So this means the sum for that input will not be displayed in output because the program will skip the steps during that particular cycle. So it is not ideal that we branch to 8. So instead of branching to 8, we branch straight to the halt instruction and the output instruction, sorry. So instead of branching to 8, we rather branch to outputs. So if it's 0, branch to outputs. So BRZ 0, what's the output line? That's line what? 6. So we branch to line 6, right? However, if it is not a 0, then we are going to store that inside this address right here. And then we take a second input again. And after we take the second input, we are going to have to do an addition. So take the second input. We add it to the inputs that was given in address 20. Remember, we are only supposed to use one memory address. So after we add it to the input that we put in address 20, the program will start cycling again, right? Yes. So then we put it here, it displays an output. That's not what the program wants from us. The program wants us to display the accumulated sum. So we have to move this output instruction somewhere else. Okay, so let's move the output instruction to a line that comes further down. So let's bring it after the branch so that it will not come during runtime. It will only come after the after the branch instruction is done. So I am changing the program line. So there's 1, 2, 3, 4, 5, 6, 7, 8. So now my output is on line 8, right? So let me edit this thing accordingly. But before I do that, let's keep going. There is more we have to do. So currently what our program is going to do is it takes an input. If the input is 0, it will branch to the line that has the output. So we'll modify the address later to meet that. However, if it is not, it is storing the input in address 20. It takes a second input and adds it to the one in address 20. We are deleting the output from here, so it doesn't output. Then it branches straight back to input again, right? It takes another input. It's if it's a 0, it displays it straight to output. But if it's not a 0, it stores in address 20. So it writes address 20 without input, with that input. And that too is another problem. So if it writes address 20 with that input, what is going to happen? It means the accumulated sum from the first time will now disappear. So that too is not ideal. So then we have to make another change here. So here's what we can do. Instead of storing in address 20 every new input that we add, why not use address 20 as our initial input? Currently, from what we have down here, we have said already that address 20 is holding a data value that is 0, and the user can, edit it accordingly. So we can try to use a load instruction. Okay, we can use a load instruction. We can tell the program that inputs by a user is taken. And we can tell the program to load address 20, right? So can take input from a user, we can load address 20, we can add the address 20 now to the inputs, and that will work perfectly. So take inputs, load address 20, and then add it to the inputs. So how do we suggest we do it? Let's load address 20 first. So LDA 20. This will mean that it will load the data value in address 20. And then now it's going to take input from the user. And after it takes input from the user, it's going to add it to what is in address 20. Are we clear? So we will put an add instruction next to the inputs here. So I'll say add the input to address 20. And after it adds the input to address 20, let's not forget our branch operation, okay? Because we'll bring that to the right place later. After it adds the input to the address 20, the program will just go further, okay? So we can ignore all the second inputs from there because it will just loop and come and take another input again. That's all there is to it. So I'm going to put my branch instruction now at the first input here, so that in case it is a 0, it's branched to the necessary this one. We are not going to edit the address yet because after we do it, we are going to see how many lines there are, then we'll edit the address accordingly. When I'm done, I'll re-explain it, okay, so you understand what is going on. Don't get too confused. So currently what we are doing is we first load whatever is contained in 20 to this side. After loading that, we feed the computer with an input. Then we add that to what's in address 20. And after adding it to address 20, we are now going to store our answer in address 20 again. So we say store in address 20. So we are trying to use only one memory address. That's why we are straining ourselves like this. Did I just do 200? Capital STA. So store in address 20, not 200, I beg. Please, the blind followers, no, please don't follow this blind man and do the same mistake. So, all right. And we store that in address 20. And after we store it in address 20, the program should just loop and then go back to load address 20. So now what will happen here? You see, there's a very genius way of writing it, right? This will mean that after we enter the input, if the input is 0, it will branch to the next address where the output is. So where will the output be? Let me submit and see where my output will be. Good. So the load address is on line 1, input is on line 0, input is on line 1, the branch address is on line 2. The output address is on line 6. Okay, so it's perfect. So this means if the input is given and it's 0, the program will branch to line 6 and it will output it before it halts. So that's perfect. We also said load 20, take inputs, add it to 20, store it in 20. So after it adds to 20, it stores the value in 20. So 20 now becomes updated with the new added sum, right? So if it was a 5, 20 now becomes 5. And then the program branches to 0. It loads address 20, which holds 5 now, right? So now it loads the 5. You take an input like 6. It adds 6 to the 5. It becomes 11. Yes, Monica.
Please slow down, why?
Okay. Okay. I'm calm. Yo. So here's what I'm saying. With the instructions that we have written right now, we are telling the program that the address 20 holds a data value of 0. And I told you yesterday that data value of 0 means that you have initialized. So then the program can be changing this data values later. So that's exactly what we are using. We're exploiting that particular function. Since we know that we have already told the program what 20 does, it is holding 0. So the program will first load the data value that 20 holds by doing LDA 20. So after it loads the data value that 20 holds, it will now receive an input from the user. So when it receives an input from the user, if the input entered is a 0, it will branch to line 6. If it branches to line 6, it means it's going to display and then it will stop. However, if the input is not a 0, so what it will do is this time is that it will rather go to the next instruction that says what? Add it to what we have in 20. So when we started, 20 has 0, enters 5, is going to be 5 plus 0. And then that's value which will be 5. 5 plus 0 gives us 5, will now be stored in address 20 according to this line. And when it is stored, it is not displayed. The program just loops and branches back to address 0. So it branches back to this side. So when it branches to this side, what happens there? We have the load instruction there. The load will load address 20. And since address 20 has been updated with the value 5, what will happen? Now address 20 will now have 5. We take an input from the user again. So maybe we take 2 this time. So then when the 2 is entered, the program will now add 2 to what is in 20, which was 5. It becomes 7. It stores 6 in 20. It branches again. It goes back to the first line. Do you understand what I'm saying? So when you go back to the first line, this time it will load the 7. It takes an input, it adds. After it adds, it stores. And after it stores, it branches again. Does this make sense now? Do you understand what I am saying, people? Hey, one minute. Okay. I don't know if you are using reactions or not, but I assume you understand. Since no one is talking, silence is consent. So let's go. So
Just
yes,
relax
this is
more. It's like you are rushing me. I'm not even hearing anything.
Oh, I'm rushing. Really? I thought today I'm sounding calm and slow. Hey, this is the slowest voice I have. Okay. We are working with time. If we don't complete the assignment today, it means I will be trained to do it tomorrow. And then the free people, you definitely won't get a chance to join again because Charlie, the stress. All right. Let me take my time and explain this one last time. The load instruction at the top. What the load instruction does is it carries data from one point and brings it to another. So it cuts the data from one point and pastes it somewhere. Okay. The instruction on the bottom here, that's the data instruction that says 20.0. It tells us that 20 holds the data value 0. It has been initialized with a 0. So whenever we load 20 as the first load, what happens is that data value is carried up there to that address. Do you understand? Do you understand so far, people? Respond if you do.
Yes, sir.
All right. So then the 0 is now loaded into. Yes, I saw someone's hand up go up briefly. Please, would you like to ask a question?
No, I wanted to react. Sorry.
Oh, okay. Thank you for your reaction. This means a lot. All right, we proceed. So the 0 is loaded into address 20. Sorry, address 20 is now loaded into the program. Now we receive an input from the user. If the user enters an input, for example, 5, the branch if 0 instruction doesn't execute because 5 is not a 0, right? However, what the user entered will now be added to the loaded address 20. So the address 20 initially was a 0. So the user's 5 is added to the 0, and then the accumulator holds the value 5. That value is now going to be stored in address 20 again. So address 20 has been updated, right? So far, so good. Are you following? I don't know if you are using reactions or
Yeah, we are following, sir.
We are
okay.
following. We are following.
All right, thank you. All right. So then we store that in address 20, and then the address 20 is updated with that value. So what this means is that, so now on this line, we are going to branch back to load 20. But since address 20 has been updated with the sum from the first operation, the address 20 will now no more be 0, it will be 5. We take a user input again due to this instruction. And then if it's a 0, we will jump all the way to the out instruction. The out instruction is going to display what the user had. And this means there is another line of code that we have to add. But before I add that, let's continue. So in case the user doesn't enter a 0, the program will just receive the inputs. After it receives the inputs, let's say 5 again, it will now add it to the loaded 5 from 20. That becomes 10. And it will store the value inside 20. And after it stores this in 20, it will branch back to the address 0. And it will keep going until the input is now 0. If the input is 0, the program will immediately branch to line 6, which is the output instruction. However, there is a little problem. You see, the program will not display something it doesn't know. When we say output, what exactly are we outputting? Right? So currently, this instruction here loads 20. If the user inputs 0, what exactly should the program executes? Huh? So then I think there's a little modification we can do. So before we do that, I'm going to run what we have here so that you can see the problem that I am also seeing. And once you see it, you tell me, I'll just tell you. So we submit that, bam. And upon submission, we now step it. So I want you to take notes because it says we are observing the program counter behavior, the accumulator updates, and the memory usage. So let's step it. It has loaded 20. So it loads the value of 20. So it's decoding and it's loading the value into it has carried it, that's 0 into the accumulator, right? Now
Hello.
we step it again. It's will now, yeah, hello.
I don't know for others, but your screen is frozen.
Um, guys, is that a shared problem or is just the only one?
Yeah, same here.
Hey, my screen is frozen. Please, is there anyone who sees the animations at least when the
No, it's not moving. Your cursor is stuck at LDA 20. It has
yeah,
highlighted.
my cursor is really?
Yeah, it has
For me, I
highlighted.
Ah,
can't I can't
Yeah,
see your screen at all.
so
I read it.
you know shit.
So then let me just quit sharing and then let's see if that fixes the issue. But if it doesn't, then it means God is just telling me to stop and go and sleep. Actually,
God knows nothing about this. Come on.
Mr. Valens.
that word.
Siblings.
Ladies and gentlemen, can you hear me?
Yeah, we can hear you.
Yeah, you're back.
Yes, please.
Also, so at first, is it that you were not hearing me? That's responding or because I was asking, but okay, all right. The Vodafone network is something else. Normally it's good, but today I don't know what's happening. Maybe I'm some bedroom lights. Oh yeah, it's Vodafone that I am using. Yes, there's a tower around here, so it's quite good here. Oh, all right. Let's let's continue. So I'm sharing my screen. This time, let me know if you can see what's happening, okay? And then say if there is a problem, let me know so that I won't waste my time going further. Can you see my screen? Yes or no?
No.
Oh my
Oh, yeah.
God. Please, how many of you can see my screen?
We can see now.
Yeah, we
Ah,
can see now.
so please, the person who said no.
It's sharing now.
No. Can you? Okay. We bless. We bless. All right. But Jay, you can see it. All right. Thank you. Let's continue. Okay. Too much time wasted on this small problem. Good. So as I said, let's run the program and see what happens. So let me reset it and start over. So currently, I was explaining what I explained. Did you get? Did you at least get the instruction explanation I gave? Yes or no?
Yes.
Hey, see, yes, now we can. Why did it take so long for somebody to say yes? Is it just me
Because
or time is moving
we
slow
cannot
today?
see your screen. Oh. We can see your screen, but you are sharing.
Yeah, now
I'm,
I can't see the
I'm
screen.
sharing what?
You've covered it
Ah,
with.
Yeah, it's
with
on and
biscuit.
off.
Ah, hold on, I'm coming. Let me see something. Then let me share window instead. I don't know if it's the screen. I know that sharing the window is always worse than sharing the screen, but if this is what will happen, let me try sharing the window instead of sharing the screen. On and off.
It's now on.
It's now on. Nah,
Yes, please.
this is quite okay. Is it still on? Can you still see it?
Yes.
Yeah, sure. Okay. So I'm asking again. Did you understand the instruction explanation? Mona said yes. So I assume Mona speaks for we all. Yes. Because I also understood what I explained. All right. Now let's step through the program and see what happens. At the first step is going to load 20. So it's going to read what's as address 20. So the arithmetic logic unit increments the program counter. Program counter tells the memory address register what address to use. Memory address register now goes to that address, reads the data value there, and brings it into the accumulator. So it's 0. So now it's done with the first one. Let's step to the next instruction, inputs. So it goes, program counter tells the memory address register which memory address to use. Memory address register tells the memory buffer register, blah, blah, blah. Good. So we enter the inputs here. Let's enter 5 and then enter. When we enter 5, it is stored in the accumulator, right? And then we step the program. After stepping the program, it runs, then keeps going. Let me just, good. Let's step it again. So it has added, okay. So it's now adding what is stored in 20. So it's reading the 0 in 20. And then it is going to add it. So it says 5 plus 0, right? And then it stores in the accumulator. It is still 5. And then we step it again. If we step it, now it carries that it goes to take the store instruction. So you'll see it will take the accumulator value and now store it in address 20. So look at the address 20. It's going to be rewritten now from 0 towards 5. So you realize that. So then the value of 20 has been updated. So it means the next time we read 20, that value is going to be carried. It's going to be carried to the accumulator for execution to happen. Me, I believe I'm talking very slow right now. So if you think I'm going fast, you should tell me. I believe I'm talking slow. So the program counter has jumped back to address 0. It has branched. So now that it has branched back to address 0, we can step again, right? So step. So then it reads the value for 20 into the accumulator. It asks us for an input, so we enter the input of 5. So let's just round this to times. In the next one, instead of entering 5, we will enter 0. We step again. Step again. It goes, takes the instruction for the addition, reads the 5 in 20, brings it to the accumulator, the ALU adds, right? So now it's 10. If we step it again, it will go and store that 10 value inside our 20, right? And now that it has it there. So now look at what happens. So in the next step, I am going to give an input, but this time I'll give an input of 0. And we expect the value of 20 to be displayed. But if what I am thinking is right, let's see if that really happens. And then maybe during this, you can learn something. It will not just be about the home task. Good. All right, so now let's enter our inputs of 0 and enter. And we step. So now see what will be displayed. I hope I'm right. So good. Turns out I really am right. So forget that I overstepped, okay? So now what do you see over here? The output is 0, but that's not the output we expected though. When we did our 5 plus 5, the output was 10. So what do you think is the problem here? And what do you think is the modification we should do to the code to be able to get it? We've written everything. All we are left with is a single line. We just have to repeat a single line at a particular point. Let's think creatively. Currently, we have all these instructions here. The load instruction. Yes. Someone has figured it out. Yes.
You have to load 20 again.
You have to load 20 again. Who was that? Is that Mr. Prince? Mr. Prince, was that you?
No, please, not me.
Who was that? Is that another Prince?
It's the free boys.
Okay, understandable. Free boys don't name themselves. Okay, that's cool. All right. So yes, we have to load 20 again. And then if we load 20 this time, we will be able to output the value of 20. So where must we load the 20? You can either load the 20 before you do the branch instruction, or you can load the 20 a little before output. So I suggest we load 20 before output. And then we are going to reroute our connection. So this time it will not jump, it will not branch. If it's a 0, it will not branch to output, or rather it will branch to the loading of 20. And when it loads it that last time, remember after a branch instruction is executed, the program counter will now continue in that sequence. So for example, in the first code, when we branch to address 8, the program counter incremented from 8 to 9 as it followed. So this means if we come here and we come to put our load instruction here, so we say load 20. like this. Then the load 20 now becomes the instruction as line 6. So if we branch, so let's submit it and then you see that's good. So the load instruction is now the instruction as line 6. So if we branch, we'll be jumping to the load instruction. So the load instruction will happen. Program counter will now increment from 6 to 7. And then when that line is executed, the output will be displayed and blah, blah, blah. So let's run the program this time. Let's run through it and then let's see if we're able to achieve what the question demanded of us. So enter our input. Let's use the 9 timetable. So 9. I was to enter. It has run. The running has been done. We enter 9 again. It has run. Incremented to 18. Enter 9 again. 27. Enter 9 again. 36. Enter 9 again. Yes, 9 timetable. Enter 9 again. What do we expect? 54. Enter 9 again. And then you see the output has been displayed. 63. And then it says what? Program halted. Ejumanesi. So this is the exact modification that you want for your code. So yes, at least I made you work for it. Yes, is it painful? Yes, it's painful. I could have just given this from the start, but I still made you work for it. At least you should appreciate it because in the long run, right? So human beings, this is the modified code you have. Before you run the code, before when all your values here in every region here are set to 0, it says take a screenshot before you do the execution. So you screenshot it first for that. After you screenshot that program, then now you will run it. And then as the looping is happening, so after the values have been updated, you screenshot that. You can screenshot that. And also after the program loops back to address 00, you screenshot that too. So that will be the screenshot during loop so that you can show that, okay, it used to be at this side, but now it has jumped to this side to prove your looping. And label them clearly with titles so that he can tell that this is for this. I don't know. I told you, I don't know how meticulous our lecturer is. So I don't know whether he's going to really go into it or he's just going to use some random sampling and then make the decisions based off of that. I don't know. And finally, after the program has terminated, like as in right now, this is the last stage. It has halted. You screenshot that too. And now it says we explain the program counter behavior during the loop. So what was the program counter behavior during the loop? So it will be observed that during the branch always loop at address 5, the program counter didn't increment sequentially from 5 to 6, but instead it jumped. So it jumped from 5 back to address 1. And then it started the sequence from that side and it kept jumping until we added a 0. And when we entered the 0, it branched once again, but this time it branched to address 6. And then it continued the execution in that sequence. So it broke the sequential flow of execution of instruction for a moment. A branch or jump to a particular address. So you describe that, okay? I'm just giving you the ideas to use. A branch to this particular instruction or jump to instruction 0. The branch instruction. And then when it did, it's now executed the program in that sequence until it came to the branch instruction again. And you mentioned that this kept happening up until the 0 was entered and the program counter value was overwritten again. So it will jump from address 2 all the way to the load address on line 6. Okay, that's for safety reasons, you can choose to modify your codes a little, you see. You can choose to modify the codes a little. So if you modify your codes, what you will do is, what do we call it? You can come all the way to this side. So inputs. Yes, good. So you can modify your codes a little by changing the address values. Okay, so changing them from 20 to something else. It says modify and it says one memory address, but I didn't really say use address 20. So you can change it accordingly. All right. And you can yeah, that's pretty much the only change I can see you making. But do it wisely, okay? Mo copy ni HMWA. All right, let's proceed. Now it says the accumulator update. So you mentioned that the accumulator value updated with every single loop. Okay, so at every single loop, when a new input was added, and then the add instruction. So when a new input was added, the accumulator incremented. When an add instruction was executed, the accumulator incremented. You can write the increments that were happening. So when I entered an initial input, the accumulator increased from 0 to maybe that input. So maybe the input was 5. And then when I hit the add instruction, it combined the 5 with the 0, and then the accumulator updated to 0. When I entered the second input, the accumulator increased to that input. When I hit the add instruction, blah, 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 in that order, okay? And then you state those things. Now, memory usage. Since we used a single memory space, which was memory 20, you will write that with every single loop, data was read from memory due to the load instruction. So data was read from memory into the accumulator. And then during every single store instruction, data was written into memory address 20. So that will be the memory behavior, okay? Data was read and written to memory address 20 with every single loop. Every load instruction did the reading, and every single write instruction did the writing. Every store instruction did the writing into memory. Is that clear, people? Is that clear? Okay, if it's not clear, try it's clear, Masa. Let's continue. So, or you cannot see my screen. Is that why you're not responding?
Can see.
Is that a queen?
We can see it.
You can see. Okay. All right. All right. Good. So you are just ignoring me. Okay, nice. All right, let's proceed. So performance analysis, 15 marks. Count the total number of instructions executed before the program halts. So, and give an instruction count. How many instructions can you see? So from 0 to 9, we have 10 instructions, right? So 10 instructions. So now it says if each instruction takes 1 clock cycle, compute the execution time at 1 megahertz per hour. So as for this one, I believe you know it, right? The man taught this in class, right? Didn't he? Huh?
He
I don't
did.
think he has.
He did. Good, good. So please, is there anyone amongst us that remembers the formula for calculating execution time when you have been given the number of clock cycles and you see there's something here? So I believe the formula is what? Instruction counts over clock rates. Is that all right? So for this particular one, is the instruction counts over clock rates. So what's the clock rate for 1 megahertz? Is what? A mega is a million. So clock rate for 1 megahertz is 1 million. So it's going to be the instruction count. So you count the number of instructions that you have in your program, and then we're going to use. So it says in our program, we have how many instructions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 instructions. So since we have 10 instructions, we are going to use that inside the working that we do. Okay, so then your formula is going to be execution time is equal to instruction counts over clock rates. And then you write your instruction counts. There are 10 instructions. So it's going to be 10 over the clock rate, which is what? 1 million. So 10 over 1 million, what answer are you going to get? Mathematicians, 10 over 1 million is 0.000000, about 5 zeros, 1. And then that is going to be your answer. Or better still, yeah, that's going to be your answer. That's seconds. Or you can use microseconds and then take away about 6 zeros from your decimal number if it will work for you, however you wish to do it. So then the second question says that, so are you listening? You work it that way, okay? So you write inside your inside your file at that particular place, you write execution time, and then you put the equal to there, equal to it. Yes, it's equal to, and then what did I say? Instruction count. So you write instruction count in full, and then over clock rates like this. Is that clear? So instruction counts over clock rates. And then your working will be execution time is now equal to, are you following? Look at this region here. I am putting them there so that you will follow that way, okay? Instruction counts, we know that, so our IC, we know that to be 5. So you can state it, like teachers like this. So instruction count is equal to, now they are sure counting and when you're 10. Man, the teacher names are there now, and even though it's AI work. And the IC is equal to 10. Now they are sure. And then the clock rate for 1 megahertz, you write it so clock rate as if you know something, but you don't know. It's equal to, then you put it there 1,000,000. 6 zeros. So a million has 6 zeros, right? Now they are sure. And then you go back and then you substitute into the formula and it's over 10 over saying 1,000,000. And then something equal to then 0 points. Now they are sure. And now the S count, yes, when you say seconds, it starts here, now they are sure. And output to me 6 zeros free on Y and the microseconds. If you can find the symbol for the micro in your word, you can use that too, just to sound fancy, even though you are not. All right. Is that clear? So this will be the working for that. And then you will move on to the next question. Next question says that, say we are using 1 clock cycle. You see, normally what we'll be doing is the formula says it is clock cycle times instruction counts all over clock rates. But because we're doing 1 clock cycle, or because we are currently doing 1 clock cycle, or the cycle per instruction, in other words, we are just doing the IC times 1. So IC times 1 will still remain the same. So you, at 2 megahertz, your number of megahertz will now change from 1,000,000 to what? 2,000,000. So your clock rate is going to change from 1,000,000 to 2,000,000. So then you will just update it accordingly. Now, question 3 says, if the cycle per instruction is 2, this will mean that not 1 clock cycle, but this time 2 clock cycles. So each instruction will move 2 times. Then you are going to have to do 2 times your instruction count. So you can update the formula, okay? It's supposed to be a CPI times instruction count rather. So let me put that there for you. So counts cycles per instruction times instruction count. A P now, okay, yeah, I forgot. So my P doesn't work. So then I'll put again. So yeah, you put a P there, okay? CPI. Or you don't know how to, okay, this is P. Right. All right, so we have CPI times the instruction count over clock rates. And instruction count is 10, clock rate is 1,000,000, and blah, blah, blah. For the second question, same formula, everything, but this time, since the CPI has been given to be 2, it will be 2 times the instruction count all over the clock rate for the first one, so over 1,000,000. And then you do the same thing for the 2 megahertz, it will be 2 times the instruction count all over the clock rate, which will be 2,000,000 this time for the 2 megahertz. Is that clear? C'est clair?
Please go
C'est
over.
clair.
Hey, why
Yes,
not?
sir.
Mona minka igbe na japata be de vimenya loko. Japata be de vimenya loko. Did you understand it? So can we move
Mr.
now?
Prince.
No, please go over the
Yeah.
CPI, please again.
Mr. Prince.
Then it means it's official. We can't complete it today. Yes. Okay, I'll go over to complete. Someone, Mr. Prince, please, who is that? You may speak, okay. Charlie Nipana offered to me, Kasa.
The sentence before the program for
Boss, your network is having bilibili.
I was asking, count the total number of instructions executed before the program halts. Is it 10?
Total number of instructions executed. It says before the program halt, right? Okay, if it's, let me see. Okay, yeah, he's right. Before program, hey, you guys should count properly, okay? So before program halts, then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 8. If it says before program halts, then we only have 8. Are you
I even
listening?
thought
That's a
it
good
was for the
observation.
program that he gave.
Okay, could be. It could be. You see, it doesn't specify as to which program he is using. You see that? It doesn't specify as to which program he's talking about. In my opinion, since the modification is the closest one that comes to the performance analysis test that follows, perhaps it might be your modified program. Perhaps it might be your modified program. Yes, Mr. Ankwanda Joseph Parkojo.
I think it's talking about the program. Hold on. Let me check my notes. I'll get back. I think I know where it is. I'm coming.
Okay. All right. So while you do that, Mona, let me re-explain to you, okay? And then listen closely. The formula for calculating the execution time is cycles per instruction times instruction counts all over clock rates. Cycles per instruction times instruction counts all over rates. How do you explain? So it says if each instruction takes 1 clock cycle, it means the cycle per instruction is what? 1. The instruction counts in this case, and now it's not before the halt, we said it right. So the instruction count is 9. The clock rates will be the number or what 1 megahertz represents for the 1 megahertz. 1 megahertz is equivalent to 1 million. What this means is in a single cycle, each one moves 1 million hertz per second or something. I don't know. Go and do your research. So 1 million. So we are going to divide the instruction counts times the CPI by 1 million. So it will be 1 times 9 all over 1 million. And then you are going to compute the value for that and you put it there in seconds. Mona, is that clear?
Yes.
Are you sure? All right. And then when the question says 2 megahertz, you're going to use the very same thing, but this time 1 megahertz is 1 million, therefore 2 megahertz will be what? 2 million. So you rewrite the very same values, and this time you will divide this by 2 million. Now it says if the CPI is equal to 2, then recompute execution time. So then if you recompute the execution time, if the CPI is equal to 2, will mean that you will now update the CPI value from your code from 1 to 2. So your formula, so it becomes 2 times instruction counts and then divided by clock rates. So 2 times the number at the top, in this case, 2 times 918 divided by clock rate. And then you jump the decimal point, the required number of times, and then you do your thing. And that's all. Okay? You, Demate. We continue. So next question for Mr. Verifying from the book, boss, Mr. Joseph. Please, have you found what you were looking for? Should we proceed till you do?
I think the calculation will be done with the codes we entered up there, the first codes before the hot.
The original ones.
Yes, the
original one. So it's not referring to our modified one, but rather the originals, right?
Yes, the original ones.
Okay, that's this one. Okay, I'd like to believe that is true too. Okay, so I think you follow his lead. So do that. So use this one. So, and then it means the instructions before the halt are input store. Input add branch 0 out and output. That makes 1, 2, 3, 4, 5, 6, 7 instructions. That makes 6 instructions. But you see, there's a problem with this one. If it's really referring to this, some instructions here will never get to execute due to this branch if 0 instruction. The branch if 0 says jump to address 8, but address 8 holds this particular value here. And it does not, once we get to this point, we basically reach the end of the program. But because we stand there, the program counter will now increment to, because it is not a halt, program counter will now increment to 9, it increments to 10, it increments to 11. So this means the number of instructions that in this particular code were executed before the halt instruction is basically 0, because the halt instruction never executed. So if it's really referring to this one, right? Do you understand what I'm saying? The halt instruction never executed. So how exactly does, are you following on what I'm saying? Because in this program, inputs is stored. Inputs is added to the stored value. Then the program now branches if the answer is 0, and it will always be 0 because 7 plus negative 7 is 0. Now the program will jump to address 8. Address 8 holds the that 0 instruction. That's just a 0 value. So it means on our little man computer, it will come and stand over here waiting for the step again. Once you step it, it will now increment to address 9, which holds 0. Increment to address 10, which holds 0. We can see that from our table, right? We can see that from our table here. You see, we can see that from our table. So from this side, 0 from 8 it goes to 9, 0, 0. So we never encountered the halt instruction. So if it says count the number of instructions that were executed, it didn't just say appeared before, but it says were executed. Unless, you know, he is just using the words, then it will mean that it can't be referring to the first program, because in the first program, the halt instruction never executed. So the instructions that were executed before halt were basically endless. They will keep going on. The halt never comes in. Does this make sense? Like, people, I want you to share your thoughts on this. For this one, it's a question from me to you, and then a question, we are sharing ideas on it. It's important that we know what the question demands.
I agree with what you're saying.
You agree?
I'm lost.
Yeah. Who said he's lost? There's no time to be lost. So that is one.
The thing make plenty for my head top also.
So I understand. You chop this evening tea before you come to class. Now maybe you don't want to eat inside. Though.
I no chop too. I don't go understand. So I don't know what work.
Okay. So hear me what I dey talk. I dey talk say, hear me out. If you talk say the question they refer to this set of instructions, I hear you. However, the question talks say count the number of instructions that were executed before the halt instruction. The word they use be executed. Executed means the number of instructions that were able to be fully implemented and used, right, before we reached halt. However, for the first program, no, if you check out well, the first instruction says inputs. It will receive input from the user. Second instruction says store at address 20. So it will store the inputs. Third instruction says input again. It will receive another input. Fourth instruction says add to the initial input stored in address 20. So it will add that. The fifth instruction says that if the answer is 0, branch to address 8. The answer will always be 0 too, because you see the question says use the exact input values. In first input 7, second input negative 7. So it means when it combines those two inputs, the answer will always be 0. Therefore, if it says branch if 0 to address 8, the program will now jump all the way to address 8. So now follow me to this side. Where's our address 8? Over here. And according to the set of data we have here, address 8 is corresponding to 1, 2, 3, 4, 5, 6, 7, 8. No, sorry, here is 0, right? So 1, 0, 1, 2, 3, 4, 5, 6. Come on. 7 and address 8 is on this line. So this line that says that's 0 is address 8. Basically, the zeros inside this box is your address 8. So when we say branch to address 8, if you encounter a 0, the program will always branch to that side. When a branch says, it means it makes a jump. It will skip the outs. Outs never comes. Yeah.
You were saying you
What,
were mentioning a
yeah, what
particular
did you say?
instruction. That is, you were mentioning a particular instruction that is at address 8, but then your this thing is not moving smoothly, so I didn't see it. What was at address 8? Can you read it out? Is it BRA00? Is that what is at address 8?
No. So no, address 8 is
Which
the
one?
dot 00. This line, this
Okay.
one. Can you see it highlighted?
Yeah, I
Good.
can see.
And if you follow me to this side in the RAM, you see and it's also a 0 value. So this means when we say branch to address 8, if 0, there will always be a 0 because we are doing 7 plus negative 7. If we get a 0, the program will now skip the output instruction. It will skip the branch instruction and also skip the halt instruction. Meanwhile, it says count the number of programs executed before halt. So halt was never implemented. It will just jump to that 0. And if you step the program again, what happens? It will now continue from address 8 to address 9. Address 9, which also contains 0 because we've not used it for anything. If you step it again, it will go to address 10, address 11, address 12. It will keep cycling and it will never come to the halt instruction. So I don't know if that matches the question that says count the number of programs executed before the halt instruction. I'm just trying to apply a little critical thinking to it to see if that's what the question really demanded. But then again, you might be right. It might actually be referring to this question. Maybe I'm overstating the thing. Yeah. Okay. So you each one's to their own. Well, yeah, they are all personal. So they do what you believe is right. I don't want to lead you astray. In my opinion, you should do the second one because the whole instruction was implemented there. But if you choose to do the first one, so you can go ahead and count. But just remember, you are counting an infinite number of instructions because the host was never implemented. But all plans, so I'll be count 1, 2. Why not? What's it say?
Hello, Mr. Prince, please, it seems you are cracking the line. I don't know if it's only me.
What?
DJ,
What you
DJ
said, I
said it's
didn't hear it. So, and let's like 2 kids away and through it like rubbish. So please say it again.
Your line is breaking. Your line is not very clear. As if you are talking, we can't hear you.
So you people should relax.
Oh, it's Officer David. Oh, please, can you hear me? Hello, guys, can you hear me?
Yes, please.
Oh, sorry. Guys, I'm sorry. See, I'm on edge and then I've had so little sleep in the past few days. So, so I'm being rude. I'm sorry. I just wanted to read the text. I'm sorry. It's like David. I didn't even know it was you that. I'm sorry. Okay. Yeah. So I was saying that I don't even know actually. Right. So guys, can you hear me clearly now? Is the network still breaking up? Yeah, yeah, let me turn off my screen. Can you hear me? Is the network still breaking up? I just did the airplane mode and the reset thing. So can you hear me clearly?
How is it like
Yeah, we
you
can hear
guys?
you.
And you see
It's
my
clear.
screen as well.
Yes, please.
That's powerful. All right. So let me just end this last few questions for you, just at least at the part C. So the next time we meet, we jump into CPU simulator, we clear that one, then we are totally done with the assignments. And while you're at it, please do the reading of the Stallings manual and then do the reading reports on that one on your own, okay? Because that one is just a reading report. If you give it to AI, it can give you the right ideas, attach it to what you already understand, rephrase the answers, get the correct answers, and understand the manual because I feel like it will be examined. And then you will use that for your thing, okay? We don't have enough time to do that. And also, the Dr. Aziz's assignment has also been done, and that expires on Friday. It's even closer. So we'll be and then, Charlie, the A's are important. So do your best. Right. So it says explain why the little man computer does not demonstrate pipelining. You see, pipelining is a function that we can examine if we are using the central processing or operating system simulator. What it basically does is this. It shows you how different instructions can be done simultaneously, like, can be executed side by side. And I'm using the right word, right, simultaneously. So side by side. However, the little man computer processes strictly one instruction at a time. This means it is unable to do that simultaneous processing of information. So it cannot do the pipelining. So you will explain that the little man computer is limited to executing strictly one instruction at a time, okay, in a fixed sequence. Even if there's a branch instruction, technically you're still using a fixed sequence. So for that reason, it is unable to run programs simultaneously, and then hence it does not demonstrate pipelining. So use these words to, yeah, you see, use these words to form your own sentences. Okay, do you understand what I just said? Family people, Alpha, do you understand?
Yes, please.
All right, thank you. Okay, whoever that was, you're a very powerful person. Okay, the last one. It says identify one limitation of the von Neumann architecture, and then we just experience what that limitation is. Especially, it happened in our very first run of the program. We realized that after we did the branch to address 8, the program now just kept running wild, and then it kept skipping to random addresses and going and going. And also, another limitation is how the von Neumann architecture stores data and instructions in the same memory spaces. This will mean that if a data is not properly addressed, it might end up being held up in a space where instruction is kept. So in our earlier days, during our very first lesson on the central processing operating system, the little man computer, some of us experienced this problem. And then we realized that when we were storing data in address 5 at the time, an instruction was already held in address 5. So when we tried to sum up the data that was stored in address 5 with the second input that we added, the answer that was being displayed was just the second input. But the data that we were trying to store and retrieve from address 5, it was not coming out. The reason was simply because in address 5 was the instruction that was on line 5 already. So as you can see, it already sequentially stores these data values inside the addresses that are assigned to them. So address 0, it holds the code for that. So it means if you come and then you store a data value, so maybe we did store in address 3. In address 3, there is already the add instruction. Therefore, there will be a contradiction, right? There will be a conflict of storage. So are we holding our address, our instructions here, we are holding our data? And instructions are always prioritized over data. So this means your data value, the computer will overlook it and throw it away like garbage. And after it does this, you will try to retrieve data that is non-existent. So these things are some limitations that the von Neumann architecture presents due to its stored program concept, where it holds data and instructions inside the very same memory spaces. It brings us these type of problems. So, use that idea and a little bit of what AI will tell you to build the understanding and then do it. Even though this is just an assignment, I feel like we have provided a lot of explanations to some of these things, and then some of you, you have left with things that you didn't come in with. So I'm glad we could help in any way we can. So now that we are on the topic of helping people, now that we have helped you, we expect your help in return. I know that even if I say it, some of you will go and then you will still not join again until there is another free class and you join. This is true. Ghanaians, we like free things. After all, wine and pay. Who doesn't like a free meal, right? However, me, I am not. Hey, network. How is this possible?
I can hear you.
Can you hear me? Can you hear me? Yeah, can you hear me? See, the network is doing something. I've never experienced. The last time this thing happened, it was because my PC was noticed it at first. It was uploading files into my OneDrive, so it had slow. It had uploaded all my movies by mistake, so it was slowing down. Time. It's just a Vodafone network that is for tonight, but normally it's very, perfect. Did you get the explanations I gave, or did that also happen after the network broke? For these three questions, if the CPI explain why, and then they identify the limitation of the von Neumann architecture, did you see that? So then the limitation, I was saying that due to the fact, okay, good. So due to the fact that, and then the particular one that we encountered was a wrong addressing. So because our branch 0 command addressed address 8, it jumped to that address, and that wrong addressing alone was enough to keep the program running wild and then going through random addresses starting from 8, and it kept executing in that order. So due to the fact that because of the stored program concepts, a random address or a wrong addressing can lead the program to go haywire. So phrase it wisely, properly. Sorry, not wisely. You're all smart. Wise. I never meant to say anybody was dumb or anything. No. I just meant to say that do it and write it as if you know, even though you don't. I'm not saying like that, but I'm just implying that sometimes we use AI for some of these things, right? And it's not like because I only said now, a new dream, right? But just do it so that the lecturer sees that you are there. So that's all I'm saying. I'm not saying you are daft, okay? Yes, I've read the messages. I am not saying that. All right. So I was saying that as we are on the topic of helping people, we have helped you tonight by bringing this lesson to you free of charge. It's not because we are kind or anything. At least me, it's not because I'm kind. It's courtesy of Mr. Evans that this lesson has been brought to all of you, the main rec, right? And then I know that, right? Yes, but me, I don't think like that. No, I think rationally. Teaching you how you have to make sacrifices for the things that matter to you. So I'm not here to teach you what charity is. I'm here to teach you that you have to pay for the things that are important in life. So please, next time, if you want to join this session, follow the numbers that you see on the communiques and join. Why? Senior man, senior woman, you are bigger than 270 cedis. You are bigger. All right. But on this note, we are going to close. Okay. I hope I was able to help you. Tomorrow we'll organize the classes again. Thank it. This network is just pulling with me.
Oh, but we can hear you.
Okay, hello there. Sorry, the network did this thing again. So I was saying that tomorrow we'll organize the classes again. If Mr. Evans wills it so, because he's the one that is giving you guys these charity lessons. If he wills it so, he will probably pay in your seat. If we will sit so, then we are going to organize the session free and then open it to everyone again. But let this motivate you so that you will come and pay. Once I make a say cry, I am slurring in my speech and I'm sleeping and I'm like my body is breaking down because I've gone nights on end. You see, so yeah, I've been busily doing things. You see, busy doing a lot of things, watching movies, So you bring the money. That's all I have to say. Everybody, goodbye. Have a great night. I hope this lesson helped. If you are still on the session, give a reaction so I know, okay, because okay, they are still here. All right. Send you a good night and then goodbye, everybody. Have a great night. Go and sleep. Go and sleep. For that. We'll be able to pass. Why? Pass.